I'm Ashvin. I work at Microsoft, and Avrilia and I together we have been contributing to Twitter Heron project. This is a streaming project, and today we'll be talking about why did we even get motivated about elasticity in streaming system, and then something about Heron, how we implemented this in Heron. So manual scaling is phase one. If any system wants to move potentially towards elasticity in the streaming world, then manual scaling could be the phase one. What we have implemented in Heron, and then Dhalion, which is work in progress, but it's about algorithmic auto-scaling, and Avrilia will talk about that later. Right. So generally speaking, if I'm talking about streaming, I'm talking about streaming application, the pipeline. Most of the applications have two kind of components. They have spouts and bolts, if I use the Storm terminology. And spouts usually ingest records into the application, and bolts will transform the records. So there's ingestion of records, tuples. So whenever you tweet something, that a spout would potentially pull it from Kafka queue or maybe file system, and then ingest into into the pipeline for processing. And bolts would transform that. Maybe it will augment it with location information, user information, or those kind of things. So that is typically when a user is creating an application, he would provide the code for the bolts and the spout. And the arrows between those two components are the streams, which are implemented by the stream processing engines. So that is where all the semantics about at least one, guarantees, checkpointing, and all the other routing information, that is what the system implements. So if I talk of Spark streaming, if I talk about Heron or Storm, then those arrows are what we're talking about. And the bolts are either implemented by the user, or there will be higher level DSL, like maybe Hummingbird, which will provide user with all this out-of-the-box components for the for these instances. In reality, when we have to handle large volume of tweets or records, then there will be multiple deployments, multiple instances of a particular component running in the system. For example, I may have 50 instances of the same Kafka spout pulling from different buckets, if I may say, and then ingesting into the system. So in reality, when the user codes it, the first phase is designing or developing the components, and the second phase is tuning those components, and how many instances of those components you want, and on how many containers or on how many physical nodes those should be running, right? So that is how typically in streaming world people think about deployment of streaming applications and pipelines. So if world was simple, this is done. But no, things become complex when you talk of real-life topologies. For example, this is one of the topologies which is generated by, which is currently running in production in Twitter. And you see, like, if I talk about, you see there's a cascading effect from one component to the other. If I increase the component parallelism for phase two, then what happens downstream? How many instances should I increase? It may not be easy to figure out that, right? If that is not difficult, then there's more complex topologies. These are generated by high-level systems, which inject more and more complex operator logic into the system. So when I talk to developers, the first challenge they see is it is very difficult to find out what is the parallelism which you should tune for the topology. How many instances should it be running, right? Anticipating component parallelism just by looking at the logical visual diagram of the topology is very, very hard. People spend a lot of time, it's like the time to market an application, time to take it to production, it just increases by weeks when you have these kind of complex topologies. The second thing we see is that in an ideal world, you'll have a constant load, an average 3,000 tuples per second coming into the system. But no, that's not the real case. When people get up in the morning, the load in the system is significantly higher. So this is a real workload. And what we see is that around 6 a.m. when people get up, they start tweeting all around, and then suddenly there's a lot of load in the system. And then I'm not including the spikes which come when there's election, there's flooding, there are natural disasters. So a lot of things change. And when these things happen, and you ask a developer, what is going to be the parallelism? It's, again, a difficult question, right? So we have talked about two challenges when I'm talking about talking to developers. And also, like, most of the time, when you think of those components, sometimes you develop those components, sometimes developers reuse it, they download it from GitHub or some component, and it's very hard to find out for each component what is the parallelism, right? So if you download it from somewhere and you have to make some code changes, you have to rebuild, redeploy it, it's gonna take more weeks, more days, every time there's a small change required, right? Suppose you tune it incorrectly, what will happen? Your support cost will go up. The SLA which is desired for a particular tuple to move across the system, across the pipeline, will be significantly higher than what was expected. So under provisioning or wrongly misconfigured topology totally ruins all the effort which has gone in developing the topology itself. And finally, most of the applications these days are running in shared environments, right? You have Yarn or Aurora shared clusters on which the topology is running. An external environment change. There could be an application which could be hogging the network altogether, or there could be hardware degradations. So given all this, what will you do? What is the solution available to the administrators of the application? Over-provisioning, right? Over-provisioning is a norm. This is what we see in production right now, that in some cases, the over-provisioning is as much as 80%. Most of the time, 80% of the codes are not utilized. And who's happy? The cloud providers, right? They're very happy about it because those challenges are very hard to solve, and because of which the default solution is to over-provision, and it's not efficient at all. So what we see is that there's scope for elastic scaling here. When I say elasticity, if the load is increasing, if there's a way to increase the number of instances, increase the number of nodes which are assigned to a pipeline, or when there is no load at night, when there is all the people are sleeping, at that time you reduce the hardware assigned to the application. So there's definitely a lot of scope for reducing the hardware cost. The administrative cost also could be reduced if there is elasticity. Given you look at the runtime performance of the topology, and based on that, you can see whether you're meeting the SLA or not. And if it is elastic, you can tune it automatically up and down. SLA, stability, all these are factors which can improve if Storm, if Heron, all these components were elastic in nature. So what is Heron? What we have done is that we have introduced one of the concepts, we have implemented elasticity in Heron. Heron, if I may say, it's Storm++, it's Storm-like. It is compatible with the Storm API, and it is a real-time distributed fault-tolerant stream processing engine. My understanding is that in Twitter, they have replaced Storm with Heron. All the topologies, all the tweets in production today, they go through the Storm to the Heron system right now. And last year, this was open source, and that is where me and Avrilia, we started contributing to Heron. So Heron is fundamentally different from Storm. The way it is designed for cloud and shared environments. Every time an application is deployed, it borrows containers from the underlying framework. It could be Yarn. When you start a Yarn application, an application master starts, and you create more containers on the Yarn cluster. So there's a shared cluster, and based on how many applications you have, Heron, and what is the size of the application, more and more containers can be allocated to the topology. So what this means is that unlike Storm, in which the Storm cluster is deployed first, and then applications are deployed on top of the Storm cluster, which means that if they don't have enough applications, Storm will still keep occupying the resources. In Heron, every time an application is deployed, resources are acquired at that particular point of time. So there is isolation at the topology level because it's running in its own application master or in Aurora. At container level, and each and every component which we talked about earlier, the instance of components is a JVM process itself. In Storm, it was each instance is a thread in one JVM, because of which there could be some sort of interference, and the isolation is not guaranteed. Heron, what we have seen is the system overhead is significantly lower than Storm, it's less than 10% compared to the time spent in executing user code. It currently provides at least once and at most semantics. Back pressure is one of the important concepts implemented in Heron. What this does is, like, if at any particular phase in the application, the pipeline, the phase is not able to execute the load, then the the routers, which are stream managers in this particular diagram, they are instructed not to ingest any more tuples into the pipeline. As a result, the pipeline is temporarily bring to a pause state, and because of which the system is able to complete whatever is in this in the pipeline right now instead of crashing out of memory and all those kind of errors. And it has a modular implementation, because of which a lot of customizations can be done. So Twitter implemented the Aurora scheduler part of Heron, and we implemented the Yarn part of, we ported this on Yarn. So you can change the scheduler, you can change the way these containers are located, and the way the instances are distributed in the system. So earlier we talked about that there are components, there are instances of components. And what happens is that when I talk about the modularity, I also talk about, I'm thinking of packing plan, which means that when you have 100 processes, and those 100 processes have to be distributed to, say, 20 worker nodes. So how do you pack them? What kind of locality information is required? What kind of, based on the DAG information, a lot of customizations can be done, and that is what a packing plan governs. So this is what we'll talk about later again. How does topology submission work in Heron? So when a user submits a topology, on the client, a packing plan is created. This packing plan essentially tells Heron, which is a client library, that how many containers on the shared cluster would be required. It starts a Heron scheduler, which could itself be running on the cluster or outside the cluster. And the system will go ahead and acquire the containers from the Heron library will go and acquire the containers. Subsequently, in those containers, processes for each of the instances of bolts or spout will be started, and stream managers are the routers which will route the data across the instances. So once the containers are allocated, once the processes are started, then the internal registration of the pipeline work starts, which means that the instances will register to stream manager, followed by stream managers registering with the topology master. This tells the topology master that the topology is ready to start processing data. So topology master will instruct the stream managers to start ingesting data into the streams, and the stream managers will start routing the data across different instances. So this is a typical another representation of the topology management process. You submit topology, you create a packing plan, resources are acquired, topology connections are made, processes are started, and when the process starts, user code will probably build a state there, which could be a machine learning state, which could be other key value, whatever state is required, right? These 4 steps are executed by the Heron system, which is like creating the packing plan, acquiring resources, installing the topology, and starting the topology. And these 2 are the user tasks, wherein the code has to be submitted and a state has to be built, right? But this is where the real problem starts, like, because these four steps are very, very time consuming. If I'm talking about the previous packing plan we saw earlier, we total had 400 containers approximately, in which there were 1,600 processes. If those particular, every time you have to acquire these many containers and start these many processes, it can take quite some time. So these are time-consuming steps. Even building state, you're hitting a remote service and you're reading the state from there. This is followed by monitoring the state if the topology is able to meet the SLA, if there's extra load in the system, and based on that, the administrator could decide that, no, I have to retune the topology. Currently, the solution is to kill the topology and redeploy the topology. What this means, all those steps which are time consuming, they have to be restarted. Essentially, this is where all these administrators are discouraged to retune the topology, and they always over-provision it, and the hardware cost keeps going up. So what is the solution? The solution essentially is that instead of killing these instances, killing all the processes, releasing all the containers back to the resource manager, if there was a way to just do the delta changes, for example, if the topology has to move from 7 instances to 11 instances in the example, if it is possible to retain all those processes and existing containers and just add new containers, start new processes in the existing space, then the delta application would be really, really fast, right? And that is what we have tried to implement, that whenever a Heron topology is restarted, at that time, try to retain as much as possible, and this significantly makes the deployment process faster. So what I'm saying is, instead of killing the topology in Storm or Heron, we added a command called update topology, which will pause the topology temporarily so that all the instances, new instances could be allocated, and then existing instances are informed that there is a topology change happening right now, and they can prepare it themselves. This is followed by unpause, and the regular process starts. So retuning becomes very, very fast. This is the manual step which we have implemented as of now, and this is minimally disruptive as what talked about. So instead of hours or tens of minutes, which was required earlier, in our experiments and in our experience, we have seen that in 1 or 2 minutes, most of the updates are successful. And because we have continued the modularity, and this could be customized also based on the experience, based on the requirements. Still, there is some work required here. We have not integrated state management into update process, which means that some sort of user intervention is required whenever a topology configuration is changed. And instead of flushing the queues automatically, what we do is we pause the topology and wait for some time, assuming that the stream managers will route all the existing tuples in the pipeline, and they will be processed. We could do a lot of things automatically. What I mean is, like we talked about this state earlier, that the topologies, the update command is issued, is pause, adding resources and all that. The responsibility of monitoring the topology is with the user right now. You monitor it, whether you're able to meet the requirements or not, is there back pressure in the system or not. The system is itself aware that there is back pressure in the pipeline. If that is the case, then this could be done automatically. So Heron can take care of monitoring that application, and it can issue the update command itself. And that is what is algorithmic auto-scaling, and my colleague Avrilia will talk about it.
Yeah, so hi, everyone. So Ashvin basically described how we can do manual updates in the topology, how we can change the parallelism in a topology manually. So in the next part of the talk, I will describe how we can do it, how we can have the system do this automatically. So, so the idea is, again, that Heron should automatically identify variations in the incoming load and react to them, essentially retune the topology on the fly so that the user doesn't have to intervene and change the parallelism. So to do that, we built a framework called Dhalion. So Dhalion is essentially a framework that sits on top of Heron and other streaming engines potentially, and provides self-regulating capabilities to them. And I will describe a bit later what I mean with that. The idea is that Dhalion will take data from Heron, and it will understand when there is a problem, and it will try to retune the topology, maybe scale up or scale down resources. So Dhalion will be open source in the near future, maybe in 1 or 2 months, as part of the Heron project. Dhalion periodically observes the state of the topology and determines whether we need to scale up or down resources. So, as I said, essentially Dhalion provides self-regulating capabilities to streaming systems. So the first capability that we want is to have a system that self-tunes itself. So as Ashvin said, it is a time-consuming process, potentially error-prone, to tune the topologies. We've seen that in production. So the idea here is that the system should take as input an SLO, maybe a throughput SLO or a latency SLO, and then automatically configure the knobs. And by knobs, I mean the parallelism, as Ashvin said, or how many containers we should deploy it, how much resources we should assign to each Heron instance, and so on. Secondly, we want to provide self-stabilizing capabilities. So the idea here is that streaming applications are long-running. They might run for weeks or even months. And as Ashvin said, during such large period of time, we observe load variations. So there could be scheduled load variations. For example, every morning we expect more tweets than in the afternoon, or even unscheduled. There's a natural disaster, there's some event happen, and all of a sudden we have spikes. So the system should be able to adjust to that, essentially reconfigure itself to manage the incoming load. And the third capability we want is self-healing capability. Because these applications are long-running, we observe during that time hardware or software performance degradation. Note that this is different from failures because failures are easy to detect. When an instance fails or a container fails, we can detect right away and restart. But it's much harder to detect when an instance runs slower than expected or where a physical node, a hardware runs slower than expected. So Dhalion helps detecting these issues and recover from them. So Dhalion essentially executes policies. So each policy has 3 phases. So in the first phase, Dhalion collects metrics from the system, in this case Heron, and tries to identify symptoms that can potentially denote that there is a problem in the system. So for example, if we see back pressure in Heron, as Ashvin mentioned, it means that some component cannot really process the load as expected, and that's a symptom that something might be wrong. We don't know exactly what it is, but it's a symptom. In the next phase, after collecting all the symptoms, Dhalion performs diagnosis generation. So it collects all the symptoms and tries to identify what is the cause of the symptom. So for example, if we see back pressure, a cause could be that we haven't tuned the parallelism correctly, so we need to scale up resources. Or another reason could be that some instance is slow and cannot process the load fast, so it causes back pressure. Or there is data skew and some instance is overloaded. So Dhalion collects all the symptoms and tries to identify what is the cause of the symptom. And then after collecting all the diagnoses, it tries to find possible resolutions, so there could be a space of potential action. So for example, we might restart an instance, we might scale up or down resources. There are many options here. At this phase, we basically select the action that seems more suitable for solving the particular problem, and we execute the action. So the architecture of Dhalion is shown in this figure. At the bottom part of the figure, you can see Heron. Essentially, the picture is very similar to what Ashvin shows. We have the containers, the instances, the stream manager. And then on top of that, we have Dhalion, which consists of 3 components. The first one is the health manager. The health manager is essentially a process that periodically executes the policy that the user defined. So we can have a policy for dynamic resource allocation of resources, a policy for meeting a particular latency SLO, and so on. So the health manager periodically executes the policy. Then we have the action log that maintains a list of actions taken by the policy, along with the timestamp and all that, so that we can debug and see what's happening in the system. And then we also have an action blacklist that essentially captures which actions were taken but didn't actually didn't actually lead to the correct outcome. So for example, we may have an action that says, I expect if I scale up resources to meet a throughput SLO, but after performing that, we didn't meet the throughput SLO. So we essentially blacklist actions so that we don't repeat failed actions again. So as you see, Dhalion it has a pretty simple architecture, and it sits on top of the streaming system. So basically, it requires 2 APIs from the system. One is a metrics API, where it can collect metrics from the system. Heron provides the metrics manager process that basically outputs metrics over time, and Dhalion exploits these metrics. And it also requires an API to perform changes in the topology. In the case of Heron, scheduler performs all the changes. So basically, if we want to add containers, scale up or down resources, we go through the scheduler component. So let's see what is the auto-scaling policy in Dhalion. So as I said, there are 3 phases. In the first phase, we collect, again, metrics from Heron, and we try to identify 3 symptoms. The first symptom is whether there is back pressure in the system. As I said before, this might denote that there is a problem in the system, and it can potentially show that we need to scale up resources. The second symptom is we observe the packets at the queues of the system. So if the number of packets is really large, so the average queue size is really large, then that's an indication that maybe some process is running slow or that the system cannot keep up with the load. And the third symptom is basically we observe at a given stage of the topology the processing rates, how many tuples are are given to the output queues for each component, and we compare. So if there is some instance that has much lower output rate than the similar instances in the same states, then that's an indication that something is going wrong with that state. So after we collect all these symptoms, Dhalion gets into the second phase. It tries to identify the reason for these symptoms. So one reason for a symptom could be resource over-provisioning. So essentially, we see that the average queue size is almost 0, which means that maybe we have provisioned too many resources for the particular topology, and even reducing the resources means that we can still meet our SLO. Then it's under-provisioning. So if there is back pressure and we see that all the components of a particular state cannot keep up with the load, then maybe that means we need to increase the parallelism at that particular state. Then we also perform diagnosis for other symptoms. For example, if there's data skew in the system, let's say one instance receives more data than the others in the same states, that could denote data skew. Or if some instances are slower than their peers in the same states, that we can also detect based on these metrics. And then we go into the third stage, where after we collected the diagnosis, we have a list of potential actions. So the actions here could be to scale down a particular component, a particular bolt, or to scale up a bolt, or to somehow resolve data skew, maybe changing our hash function, or restart slow instances in new containers and see if they will start improving better. And finally, after picking up the particular action, we invoke the resolver. So with this policy, we are able to scale up and down resources, and note that we are able also to identify. So we don't blindly scale up resources. Maybe the problem is somewhere else. Maybe there's data skew or some instances are running slow. So we are able to identify that so that we don't unnecessarily increase the resources used by a topology. So we have some initial results. This is a simple example, a simple topology, where basically we have the topology as steady state S1, and we decreased the load of the topology by 20%. So we sort of decreased by a small factor just to test if Dhalion is able to understand that this change has happened. And as you can see here, Dhalion actually understood that, and it scaled down resources twice. So basically, we have two types of bolts in this topology. There's a problem with the figure there. So there's the counter bolt and the splitter bolt. So we scaled down both the counter bolt and the splitter bolt. And as you can see, the throughput of the topology remained the same, which means that it was a good decision to scale down. We didn't decrease performance. So we reached steady state S2. And then after some time, we increased the load by 30%. And we try again to see, we expect to see Dhalion understanding that and scale up resources, which actually happens. So Dhalion scales up resources 4 times until it reaches steady state S3, where basically we don't observe back pressure and we have the maximum throughput. And here you can see basically how resources change over time based on Dhalion with different steady states, S1, S2, and S3. So you can see that over time, it reduces or increases the parallelism as needed. Another policy that we can have is essentially how to satisfy throughput SLOs. So the idea here is that we want to eliminate the tuning phases, especially before getting the topology into production. So what happens here is that the user submits a topology with parallelism 1 at all levels and a throughput SLO. For example, I want to have 1 million tuples per second out of the system. So Dhalion should help reconfigure the topology so that you can meet this throughput SLO. So how it does that? It automatically tunes the number of spouts and bolts so that the SLO is met. Essentially, this policy reuses the mechanism of the auto-scaling policy, but we have implemented additional symptom detectors, diagnosers, and resolvers. And here you can see some results. So basically, we started with a topology with parallelism 1 at time 0, and then we set the throughput to a little more than 4 million tuples per second, and you can see that Dhalion essentially increases the resources until you meet that. So here you can see that it takes some time to actually meet that. The reason is that we had a constraint in the system not to increase the resources by more than 4x at a time. So because of that, we had extra steps. But still, this time is reasonable for pre-production phase, where you basically try to tune the topology. It takes days now. Here it takes about 90 minutes. No, less than that, 70 minutes. So what are future plans? So first, we want to open source Dhalion and the auto-scaling policy as part of the Heron project. And then we want to use Dhalion to enforce throughput and latency SLOs and to auto-tune Heron topologies. That we expect that to help a lot the developers. And then we want to combine scaling with stateful stream processing. So this is currently under work in progress, and we have pull requests already for that. So here you can see how you can get involved with Heron. There's the GitHub repository, the Twitter account. So feel free to ask questions and also find us after the talk to talk more about Heron. So, and with that, I'll be happy to take questions.
This is being used by Twitter. Is this being used by Microsoft at all? I mean,
so currently not yet, but we've been working on that for 1 year. So our lab basically works a lot on open source, and this is one of the projects we are actually invest, but it's not yet in production.
Okay.